Now that you have an understanding of the types of chemical reactions, let's talk about a little of each one. First off, a precipitation reaction is a reaction in which two solutions are mixed in a precipitate forms. And a precipitate is any insoluble solid. So for example, when I mix potassium iodide and lead nitrate, I end up with lead iodide, which is this yellow looking substance here. If I wanted to separate the lead iodide, which is insoluble, from the rest of this solution, I could separate it by filtering it through a process called gravimetric analysis. I could filter it and then take its mass, and then using stoichiometry, converting from one product to another, I can figure out the concentration of the original sample, or I can figure out my percent yield, all very useful information. And it's all based on the solubility rules. So you must know these solubility rules for no other reason other than I will never give them to you ever again. So first off, most alkali metals that form a salt are soluble. Any halide, with the exception of silver, mercury, or lead, is soluble. Anything that forms up with fluorine, with the exception of group 2 metals, so barium, magnesium, calcium, strontium. Sulfates are usually soluble with a couple of exceptions, and carbonates, phosphates, and so on are insoluble, except for if they're with an alkaline metal or ammonium. Once you understand solubility rules, you can write an equation a couple different ways. First off, the equations, the way that you've been seeing them so far, are what we call complete balanced equations, or molecular equations, which shows everything as a molecule, even if it's soluble. For example, all sulfates are soluble. Hydroxides are also soluble. So when these two are actually in solution, they're actually ions. And when they form up on this side, sulfates are soluble. This is also an ion. So this would be the complete balanced equation, or molecular equation. However, you can take this and show the ions that form from it, and that's called the complete ionic equation. In a complete ionic equation, you show the ions as they are in solution. Since sulfuric acid is going to break up, it is a strong electrolyte, it will break up into 2 hydrogen ions and sulfate. There should be a plus between here. Let me fix that. Same with sodium hydroxide. Strong electrolyte, going to break up completely. Sodium sulfate, going to break up because it's soluble. However, water is not soluble. Water is a liquid, so that's why it's symbolized with something different rather than AQ. Water is a pure substance. So that would be the complete ionic equation. Now you can take the complete ionic equation and cancel out things that appear on both sides of the arrow. So I have 2 sodium here and 2 sodium here. They're going to cancel out. Same goes with sulfate. Sulfate appears on both sides of the equation identically, so we can cancel it out. Once we've canceled them out, we can write the equation as it appears, and that will give us our net ionic equation. A net ionic equation includes only those compounds and only those ions that go into forming a final product that is not soluble, or something that is different. Everything else that we canceled out, so the sodium and sulfate, are what we call spectator ions. They're sitting on the sidelines cheering. They're the cheerleaders at the football game. No offense to the cheerleaders, but they have no function in the overall game itself. They are just sitting on the sidelines. And notice that there is a conservation of charge in net ionic equations. We have a positive and a negative. Sorry, had to fix that. We have +2 plus a -2 gives us 0, so this side has a charge of 0. On this side, We also have 0 again, no charge on this side, canceled balance charge on this side, so 0 to 0. There is always a conservation of the charge in a net ionic equation. It's one way you can check to make sure you have a balanced equation. Lastly, in acid-base reactions, we're going to simply define an acid as any compound that when in water produces the hydronium ion, or hydrogen. This is the Arrhenius definition. So if you remember from general chemistry, this is not a full definition of acids, but for right now, just anything that produces hydronium in solution is an acid. And on the opposite side, anything that produces hydroxide in solution is a base. Again, for right now, this is a very basic definition of acids and bases, but for right now, that's what we're going to talk about. A neutralization of acids and bases is when the moles of acid equals the moles of base, because then you're going to produce water, which is not necessarily going to mean it's going to have a pH of 7. When we get to buffers, you're going to see where that's not necessarily a true statement. So the formula to figure out the formula that goes with acids and base reactions is that the moles of acids times the number of hydrogen ions equals the moles of base times the number of hydroxide ions. And we use that formula particularly when we're doing a titration. In a titration, we add acid or base from a standardized solution to what we are trying to find the concentration of, the opposite, either acid or base. And we know when we reach the equivalency point, or the point at which the moles of hydroxide equals the moles of hydronium, because an indicator will change color. So we look for a color change in a titration reaction. Lastly, standardization is a procedure for establishing the exact concentration of a certain reagent. And we're going to be using this in one of your labs coming up when we get to acids and bases and buffers. We're going to be talking a lot about standardization, but for right now, basic definition. Standardization is a procedure for establishing the exact concentration of a reagent. You need to know that number of moles of hydrogen times the number of hydrogen equals the moles of hydroxide times the number of hydroxides. And lastly, we come to oxidation and reduction reactions. There are a couple terms you need to know that go with oxidation and reduction reactions. First off, what is oxidation? Oxidation is a loss of electrons. So when something increases in charge, it is oxidized. When something's reduced, it gains electrons. Its charge is going to go down from either being positive to being 0, or even possibly down to negative, or from 0 going down and becoming negative. It is being reduced because it's gaining electrons. Remember, each electron is a -1 charge. We can remember this by oil rig. Oxidation is a loss, reduction is a gain of electrons. We also can do Leo goes Gur. Loss of electron is oxidation, gain of electrons is reduction. However you remember it, just make sure you get it straight. An oxidation number is the charge assigned to an atom. So for example, if I was talking about a oxygen ion, that would be O2-, where the 2- is the oxidation number. Now in your notes and in class, I'm going to try my best to always put the sign after the number for if it's an oxidation number. So this would be O2-. It doesn't matter if you put the sign in front or behind. It's simply a matter of what you were taught. So oxidation number is simply the charge on an atom. An oxidizing agent is anything that is reduced because it's going to force something else to be oxidized. And a reducing agent is anything that is oxidized because it's going to force something else to be reduced. These terms may, again, this is hearsay, but I heard at the conference that these terms may be going away. However, they are not gone away yet. So you need to know that an oxidizing agent is something that causes something to be oxidized by being reduced itself. So in a reaction, if I say what is the oxidizing agent, you find what was reduced, and that's your oxidizing agent. If I ask what is the reducing agent, find out what was oxidized, and that's your reducing agent because it's forcing something else to be reduced. Now there are a couple rules that go with assigning an oxidation state to something, and you should know most of this already. None of this is going to be exactly new. It's just going to be a good refresher because this is what we did at the end of the year with your pre-AP class. First off, the oxidation state of any element in its elemental form, meaning it's all by itself, is always zero. An element by itself, its oxidation state is zero because it's neutral unless it says otherwise. The oxidation state of monatomic ions is the same as its charge. So the charge it gets, you can look at the periodic table. Oxygen is always a 2 minus. Even when it's in some compounds, it's always going to be a 2 minus. Oxygen's kind of your go-to guy. If you see oxygen, you can say that's minus 2, and I should be able to figure out the others based on that. If hydrogen's in the front of something, it's always plus 1. If hydrogen's at the end, it's a minus 1. This is very rare, but sometimes it happens. Hydrogen will have a minus 1 oxidation state. And the sum of all of your oxidation states has to equal 0 for a neutral compound. If this compound's not neutral, say it's one of your polyatomic ions you should be memorizing, then the sum is going to equal the charge of the ion. So the easiest way to do this would be to simply sit down and do one. So let's put up a couple of these. So let's do carbon dioxide. First off, again, oxygen's your go-to guy. Carbon dioxide, oxygen's there, so oxygen is always a 2 minus. Now I have two carbon dioxides, or I have two oxygens in carbon dioxide. So overall, oxygen is contributing a minus 4 charge. And we know that this is a neutral compound because there's no charge out here. Carbon dioxide, you're not walking down the hallways here at Mentorville and getting shocked by carbon dioxide gas. So we know that this must be a neutral compound. So it becomes x minus 4 equals 0. What does x have to be? Well, x must be a 4 positive. So since there's only one carbon, that one carbon has an oxidation state of 4 positive. Next, sulfur hexafluoride. Fluorine is always a minus 1 when it's in a compound. So that's 1 minus for fluorine. If I have 6 fluorines, each fluorine is contributing minus 1. So overall, fluorine is contributing a minus 6. So 6. So since again this is a neutral compound, we didn't have any charge next to it. So this must mean that x minus 6 equals 0. What does x have to be? Well, x must be 6 positive. Since I only have one sulfur, that one sulfur is contributing that 6 plus, so sulfur's oxidation state must be 6 positive. Alright, last one. Nitrate. Nitrate has a minus 1 charge, so that means that we're not going to equal 0 here, we're going to have to equal 1 minus. Again, oxygen in a compound, oxygen is always our go-to guy. Oxygen is minus 2. If I have 3 oxygens, each is a minus 2, so that means overall oxygen is contributing a minus 6. So the question becomes, what minus 6 is negative 1? Well, that must be plus 5. So nitrogen has an oxidation state of 5 positive, or nitrogen is contributing a 5 positive to this reaction. So it must mean that that one nitrogen has an oxidation state of 5 positive. So this problem asks us to identify what is being reduced and what is being oxidized, and then tell what is the oxidizing and reducing agent. So before you can do that, write out the problem, and let's first break it into two separate things. I have aluminum that's going to become aluminum iodide, and I have iodine that's going to become aluminum iodide. So I'm going to break this into two half reactions. I'm going to show half of the reaction at one time. So now I've broken this into two half reactions. Aluminum becoming its product, iodine becoming its product. Let's assign oxidation numbers to aluminum and iodine in the product as well as when they're elemental. So here we have aluminum going from being aluminum 0 to aluminum plus 3. Well, how would it do that? It would have had to lose electrons. Where did those electrons go? Must have went to iodine, because iodine goes from being 0 to minus 1. Since aluminum lost the electrons, it's oxidized, and since iodine gains electrons, it's reduced. Whatever is oxidized, that's the reducing agent. Whatever is reduced is the oxidizing agent. The end.